Now, this is also often called the governing differential equation of this spring mass damper system, which is now subject to this sinusoidal excitation. Okay, so excitation because it is a force that is being used to excite the system. All right, and sinusoidal because we have a cosine function here. All right, omega is a parameters, which means it's a variable. It can be, for example, 1, 2, 3, 1.5, 100.6, etc., etc., etc. Okay, the reason we want to make it a parameters is we want to understand the impact of omega on the response of this spring mass damper system. Let's first review what we did before. How do we determine the so-called force acceleration of these spring mass damper systems? We use a technique that we learned in the course of engineering mathematics, which tell us based on the method of undetermined coefficients. We know that if the forcing function is made of a sinusoidal signal, then we assume its particular solution to be a linear combination of the cosine and sine functions of the same frequency. All right, okay? And to determine what A and B should be, we just substitute this representation into the equation of motion or into the so-called governing differential equations. To do that, we need to take the first derivative and the second derivative of this representation. And that by plugging them into this equation of motion, we come out with this equality. To this equality to be true, the coefficients of the cosine omega t on the both sides of this equality has to be the same, which means epsilon has to be equal to this term inside the bracket, which is this. And for the sine wave, okay, for the right-hand side of the equality, there is no sine wave. So its coefficients for sine wave is 0. However, on the left-hand side of the equality, within this bracket, the coefficients for the sine omega t should be this. Okay, now here we have two conditions, two equations, two unknowns, which are A and B. So A and B can be readily solved, and these are the results for A and B. All right, now by introducing omega 0 as natural frequency, which is the square root of the ratio of spring constant to the mass, okay, we can rewrite these two expressions as this. Apparently, A and B is a function. Both of them are functions of omega. Please remember, omega is the frequency of our excitation. All right. Now, we want to go one step further so that the response of the system can be represented not in this format, but in this format. Okay. Why do we want to do that? Because here in the original format, we need to deal with two sinusoidal functions. One is cosine, the other is sine. Okay, we want to simplify the matter, so we want to introduce a new representation which involves only one sinusoidal signal, which is cosine. How do we do that? Okay, last time I didn't do such a good job in telling you how do we go from here, okay, to here, okay, to here, all right? Let's say originally this is what we have, all right, with sine and cosine. So what we need to do is first refer to this right triangles, okay? So since it is a right triangle, the angle here is 90 degrees, okay? And AN and minus BN, noted that I put minus BN here on purpose, okay, on purpose, right? Apparently, if this is the case, BN has to be a negative number because the length of a side of a triangle cannot be negative. In any way, if this is AN and this is minus BN, then this is apparently N squared plus minus BN squared. And then after having the sum, you take the square root. Now, what I want to do is that based on the information provided by this right triangle, I would divide everything by n squared, the square root of n squares plus bn squared, all right? But to cancel out the effect of this division, I need to multiply everything with the square root of n squared plus bn squared. Now, the reason I do that is for this part, based on this right triangle, we know that this is essentially cosine theta. And similarly, for this part, from this right triangle, this is essentially sine omega n. And then we use this equality, which we learned. I think you learned this equality in junior high school. All right? Now, x is here, and omega 0t, and y is theta, and here. And what is theta? Again, based on this piece of information, you know that tangent theta is essentially minus bn over an, right? We learned this when we was in junior high. As a result, the entire representation, the entire expression can be rewritten as this, where Cn is this, the square root of n squared plus bn squared, okay? And this is, and this reduces to this, all right? Okay, we will see this two representation again in the later part. I think it's later part of today's course, okay? All right, if everything goes well, all right? Now, the important thing here is that once you completed this conversion, you will realize that Cn, since An and Bn are both functions of omega, and since Cn is this, the square root of n squared plus bn squared, so it is clear that Cn is a function of omega, all right? Similarly, the angle here is a function, also is a function of omega. Remember, omega is the frequency of the excitation force, which is being applied to the spring mass damper system under consideration. All right? So with these two expressions, I can generate these plots, okay? And for this part, this is actually the amplitude spectrum of the system. And for this part, this is what we call the phase spectrum of the system. And when you put them together, they represent the frequency response of the system, okay? I think, why do we call it frequency response? The term response here is easy to understand because it represents the result of the excitation. Okay, how system respond to that external excitation force. Okay, and the reason why we call it frequency response, because we take the parameters, the frequency parameters into considerations. From this response, we know how our spring mass damper system respond to impulse with the same, respond to sinusoidal impulse with the same amplitude but different frequencies. All right, and this is very important. Understanding the frequency response of the system is very important because it will give us many pieces of the information of how the system behave. Okay, all right, we will talk about that later. But first, let's go one step further to talk about frequency response. There is one idea which we talk about, I think last week. That is the idea of bandwidth. Okay, now this is one way to define bandwidth. Okay, note that this represents the amplitude spectrum of a system. For example, a spring mass damper system, and this omega is the frequency of the excitation force, and this is C omega. All right, okay, which is the amplitude of the response of the mass. Okay, now we will talk about dB later, but essentially dB is 20 log C. Okay, let me just write it down. 20 log C. All right, now, so what do we want to talk about? Bandwidth, because bandwidth come from frequency response. And as I just described, frequency response give us many information about the behavior of the system. One piece of information is bandwidth. Okay, in control system, bandwidth refer to the frequency range over which a system can effectively respond to the input signal or disturbance. Okay, now let me give you a real life examples. Okay, to visualize the idea of bandwidth. Okay, imagine you are asked to follow a moving pointer whose position varies like a sinusoidal wave, moving smoothly back and forth. So if I am asked to do that, I need to move my body to follow the motion of the pointer. For example, from this end to this end. All right. When the pointer moves slowly, which it means it moves in low frequency, I can easily follow this motion and match its full range. So I can go from one end of the blackboard to the other end of the blackboard in time. I can follow through all the time. I can match its full range. When I say full range, I mean the full range of the motion of the pointer. Now, but as the pointer moves faster, that is, when it operates in higher frequency, it becomes more difficult to keep up, right? Because there is a limit on my moving speed, okay? Now, your motion starts to lag behind and fall short of the amplitude of the pointer's movement, because if I'm not moving, if I cannot match the moving speed of the pointer, it is possible that the location of pointer is here, my body is still here because I cannot move fast enough. And when the pointer switch is moving direction to this end of the blackboard, what I need to do is I have to switch my direction so that I can follow the newly moving direction of the pointer. So the final result is that I will not be able to match the full length of the motion of the pointer when the pointer is moving in high frequency, all right? So the result is I fall short of the amplitude of the pointer's movement, all right? That means here, okay? Here, 0 dB means C is equal to 1, which is here, all right? That is whatever F0 is, C is exactly the same as F0. Exactly the same. And that is what we want, because input is the command, and the output is what we want, okay? So for the command, for the actual output to be exactly the same as the reference input, and that is the basic goal of control. And for that to be true, at least for this sinusoidal excitation signal, C, the ratio of C to F0 has to be 1. But this is not always true. It is true only when omega is small enough. Why is that the case? This is an illustration with a real example to tell you why that is not the case, okay? Eventually, at some frequency, your ability to follow the pointer diminishes so much that your response is no longer effective. That means the frequency property is here, and the value of my C is become very, the value of the ratio of C to F0 become very, very small. In that case, that means my system is unable to effectively respond to the input, respond to the reference input, okay? My system cannot effectively respond to the reference input because it cannot match, it cannot match its full range motion. So eventually, at some frequency, your ability to follow the pointer diminishes so much as your response is no longer effective. This makes the limit of your bandwidth. Okay, so that's the limit of the bandwidth. Now, let's make this concrete. Suppose a pointer motion has an amplitude of 1 unit. At certain frequency, I, as an older person, might only be able to follow about 50% of that amplitude. That is, I cannot follow through fully because my response speed is limited. A younger students like you with quicker reflexes, okay, and more energy, okay, might still achieve 80% of that amplitude at the same frequency, all right? That means, let's say, let's say this is my bandwidth, okay? And your bandwidth probably look something like this. So it extends further to the left. I mean, the bandwidth will extend further, I'm sorry, not to the left, to the right, okay? Which means as a younger person with quicker reflexes, with more energy, okay, with faster, with better ability for fast movement, okay, you have a higher bandwidth than me, all right? So, okay, so this illustrates a higher bandwidth system, like the younger students, can follow faster input changes when greater accuracy and with greater accuracy and completeness, while lower bandwidth system like me, which is an older person, struggle to keep up and produce weaker response. All right. So that is the idea of bandwidth, and you can generate bandwidth from the frequency response of your system. Okay. So in frequency response analysis, the bandwidth of a closed-loop system is usually defined as the range of frequency from 0 to some cutoff. This is the cutoff point, okay? Now, where the magnitude of the closed-loop frequency response remain about a certain level, okay? Here, the certain level is minus 3 dB, larger than minus 3 dB, which is about 70% of the low frequency values, okay, or 70.7% of the input sinusoidal signal amplitude. All right. Now, I want to make some remarks about bandwidth. I think one of the most important things of bandwidth is it is an excellent measure for us to quantify the speed of response of the system. A system with a larger bandwidth can track higher frequency, faster reference signals, and is more capable in rejecting higher frequency disturbance. It can respond faster, okay? It can deal with higher frequency input signal and input disturbance, okay? So roughly speaking, bandwidth is proportional to the speed of response, roughly speaking, okay? A system with a larger bandwidth usually often means that system has a faster frequency. Faster speed of response. So bandwidth, speed of response, bandwidth. Essentially, you can think of them as two sides of the same coin, okay? Two sides of same coins. One is from the perspective or time domain, okay? And the other is from the side of frequency domain, all right? So connection to stability, it also has something to do with stability. Increasing bandwidth usually improves tracking ability, but can reduce stability margin. Okay, we have not yet talked about phase and gain margin, but you can certainly understand the faster I operate, the less stable I am. Okay, so the speed and stability are usually something we need to balance. So designers must balance responsiveness, which means this term, of course, represents speed of response with robustness. Okay, this means how much room I have before my system will run into instability problem. I need some tolerance. Okay, two more remarks about bandwidth. The first is a higher bandwidth system will also pass more measurement noise. Okay, therefore high bandwidth improved tracking make the system most sensitive to noise. Okay, once you have noise, and the frequency components of noise usually concentrate on high frequency band. So high frequency noise can, because if a system has a larger bandwidth, then those high frequency noise will effectively excite the systems, which means a system with higher bandwidth is more sensitive to noise. Okay, now practical rule of thumb of choosing a bandwidth. Bandwidth is often taken as an approximate upper bound of the frequency input the system can track with small steady state error. So you can try to increase or enlarge the bandwidth until the steady state error become undesirable, okay? We will look into this problem later, all right? Now, remember that the topic here is frequency domain analysis for signal, okay? To do that, we need to use a very important mathematical tool, that is Fourier series. Remember that in conducting time domain analysis, we also introduced a very fundamentally important mathematical tool, which is Laplace transform. All right? Okay, here, to conduct frequency domain analysis, we need to use Fourier series. I'm pretty positive you learned Fourier series when you took the course of engineering mathematics. When I took the course of engineering mathematics, I also studied Fourier series. But at that time, Fourier series is nothing but the mathematical techniques, mathematical methods. I have no idea how to apply Fourier series to real-world problems because I don't understand its physical meanings, okay? Now, in this course, I will do my best to help you understand why Fourier series matters, what is its practical values for us engineers. Now, Fourier series, let's first set up the stage, okay? And the beginning, the first thing we want to emphasize here is that Fourier series was originally designed to represent periodical signals or periodical functions. What is a periodical function? Any function, no matter what it appears to be, what is its morphology of its waveform, it doesn't matter. As long as it satisfies this equality for every x, it is a periodical signal, all right? Which means the value of that function will repeat itself after a certain amount of, let's say, time, all right? Okay, so P here, in this particular example, apparently is the period of this function, okay? Because the value of that function repeat itself every P, okay? Now, these are numbers of periodical functions. And as you can see, sine and cosines, regardless of their frequency, they are all periodical function. One special property of a periodical function is, by definition, it will last forever. That is, it will go from minus infinity to positive infinity. Why? Because it always repeats itself. So it never diminishes, it never diverges, it will also never converge, okay? It is just simply always there, okay? So periodical function never end, never end. It will just go all the way to eternity, okay? All right. All right, now let me introduce another important variable, which is radio frequency. Now, once you have a period for a periodical signal or periodical function, you have a frequency, all right? Frequency is apparently the one inverse period, reciprocal of period, okay? Why? Because by definition, frequency is the number of periods per time unit. For example, if you have 10 periods within 1 second, then if the period is 0.1 second, all right, then you have 10 periods in 1 second. And therefore, the frequency of this periodical signal is what we call 10 hertz. Very easy to understand, okay? And F here is the frequency in hertz. That is cycles per second, or you can say periods per second, okay? But instead of using F, usually in the area of control, we prefer use radio frequency, which is defined as 2 pi times F. So radio frequency with a sample of omega measures how fast something oscillates or rotates. But instead of cycle per second like hertz, it is expressed as radius per second. So its unit is really radian per second. And one full cycle apparently is 2 pi radians. How do we visualize that? Think of it this way, okay? Let me connect radio frequency with angular velocity, okay? Assuming that you have a clock here, okay? And one period of the clock motion means the pointer has to move one complete cycle, right? And angular velocity represents its rotation speed of the physical object, such as the pointer of this clock. And radio frequency represents oscillation speed of the sinusoidal signals. Both use the same units, which is radio per second. So in using radio per second, I can think of it like one period is like moving the pointer one round, okay? By moving the pointer from the beginning to the end once, that represents one period. And apparently the moving speed is characterized by the angular velocity with a unit of radio per second. So that's how we connect the dots, okay? Radio frequency, speed. Radio frequency, speed. When we say speed, we refer to angular velocities, okay? All right, now, remember, as I just said, the focus here is Fourier series, and this is a Fourier series representation, okay? This is the original signal. This is its Fourier series representation, okay? Now here, omega 0, what is omega 0? Let's assume here, x of t has a period of t, which means x of t equal to x of t plus capital T for every t, okay? This means I'm sorry. I apologize for my poor handwriting. Okay. I did not invent this sample, okay? So it is commonly used mathematical samples to represent for every, all right? Okay. Now, if this is the case, P, let's say T, capital T is the period, then here, omega 0, which is defined as 2 pi to T, is what we call the fundamental frequency. Usually we ignore the term angular. Is the fundamental frequency of this periodical signal, all right? Keep that in mind, fundamental frequency. And A0 is the DC component, okay? What is a DC component for periodical signal? It is essentially the average value of the signal, which means this, okay? This x of t, we integrate within one period, okay? And now, why don't we want to go why do we restrict ourselves in one period? Because it is a periodical function. Okay, if you want to go here to here, you just do the same thing repeatedly. Okay, it doesn't provide any additional information. So when it comes to the average value, all you need to do is concentrate on the time response of x of t within one period. Okay. Another thing is it doesn't have to be go from 0 to t. Okay, it can go from any given particular, let's say t1 n to t1 plus t, as long as it covers one complete period. Because when it comes to a periodical function, there is no such thing as the end of the period, the beginning of the period, because every point can be the beginning of a period. Every point can be the end of a period. Okay. The only thing is to be an end and to be a beginning of a period. The distance between these 2 points has to be capital T. That's it. All right. So why is A0 an average values? Because if you look at this representation, we still have cosine and sine to consider, right? The reason why is cosine and sine always, its value always come between -1 and +1. So if you integrate them, the positive and negative values of sine and cosine will cancel out with the other. So eventually it will become 0, which means you integrate this, you will definitely get a result of 0. Okay, you can do it by yourself, but it is just mathematically true. Okay, now A0 is the DC component, and DC component for a signal is simply the average value of the signal. And AN and BN are what we call mathematically Fourier coefficients. And they represent the amplitude of the cosine and sine components of the nth harmonic. Okay, the term here you need to pay special attention is harmonics. Okay, so when n is equal to 1, we are dealing with cosine omega 0t and sine omega t, which are the frequency components located at omega equal to omega 0s. And that is the first harmonic of this signal. And the second harmonics, of course, correspond to A2 and B2. Okay, so that is how we visualize or conceptualize harmonic. All right, now let's go one step further after the introduction of DC component. Here, what we learned from the course of engineering mathematics, we can use these two equalities to help us determine Fourier coefficients AN and BN. Okay, I don't want to go to the mathematical process to prove these two equalities are true. Okay, you can always go back to your textbooks of engineering mathematics for the background, for where do these two results come from. All right, now the topic here is Fourier series for signal processing. Okay, why we want to start this topic? The reason is that we want to understand why do we want to use Fourier series in the first place? Why do we want to employ such a representation? Because in the beginning, at least on the surface, it doesn't make sense. Why it doesn't make sense? Let's say xt is a function. Let's say e to t. It is an exponential function. Such an exponential function is well defined. We know its derivative. We know its how to integrate it. We know a lot of things about this exponential function. If this is the case, why do we want to have its Fourier series representation? Because when we need to deal with these Fourier series representations, we need to deal with infinite numbers of terms, right? And that apparently increase the complexity of the entire process, okay? Why not just deal with one simple, well-defined, well-understood function and jump into this infinite series, which involve infinite numbers of terms, okay? Why do we want to have a Fourier series representation in the first place? And the answer really lies on this process. Because with Fourier series, when dealing with signals, we can perform this so-called three-step procedure, which consists of analysis, modify, and finally synthesis. So one of the bad things about Fourier series representation is exactly first, analysis, which means decompositions. You break down a periodical signal into a sum of simple sinusoids, each with a clear frequency, amplitude, and phase. This gives insight into the signal spectral contents. Okay, whenever you see the term spectral, it means you discuss things in frequency domain. Spectral content really means, what it means is the frequency composition, all right? Is the content in the frequency domain, all right? So how do you understand, let's say, how do you understand a materials, a composite that you never saw before? You perform analysis by breaking it apart, okay? To understand what elements that composite material has and how many elements, chemical elements, and what is the percentage of each of those elements. Let me give you another example. How do you understand how a machine works? One of the possibilities is you just take the machine apart, okay? And you examine the components of the machine one at a time. By understanding the functionality of each component, you then will have a better idea of how those components interact with one another. And finally, you will have a very good understanding of how the machine works. But to do that, you need to break that machine into pieces, into different elements, okay? So you can study one element at a time and then put all you learn from each and every of those elements together to help you have an overall complete picture of how that machine works. Same thing happened here. A signal is presented right in front of me. To understand the nature of that signal, I need to break it down into fundamental elements. And that so-called fundamental elements are actually sinusoidal signals of different frequency and different Fourier coefficients, okay? Once you have its Fourier series representation, the next thing you can do is modifying, also called processing. We can selectively adjust components. For example, remove high frequency notes, okay? For example, boost certain harmonics, because let's say you are listening to a music and you are a big fan of rock and roll and you prefer big bass, bong, 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 bong. So what you need to do is you adjust the low frequency harmonic, all right, to make, let's say, AM, BM larger for smaller n, okay? Because n equal to 1 correspond to omega 0 component and n equal to 2 omega 0 components. You just identify the frequency range of the base band, okay? And then you enhance, you elevate the magnitudes of these coefficients, okay? And by doing that, I multiply my signal, okay? And I can also filter out unwanted parts in this way, okay? And then remember, this is a three-step process: analysis, modify, and the final step is, of course, synthesis, which means reconstruction. By recombining, acting back the modified components, we can reconstruct a new signal that matches our needs, okay? So that is the fundamental goal of signal processing. In order to process signals, you need to use Fourier series, because with the assistance of Fourier series, you can actually see the frequency components, okay, of that signal. And by changing one component at a time, you can modify the signal to match your needs, all right? So, for example, by using this so-called decomposition, I should say three-step process, what can we do? For example, practical applications, including first, filtering, remove, or amplify certain frequencies. Remember, filtering does not always mean removal, okay? It can also mean amplification. So filtering is not a process of subtraction or division. It's a process of making it bigger or smaller. In other way, okay, it just means that you can change the frequency, amplitude spectrum of that systems, okay? Compression, keep only the most significant components. Okay, in theories, this Fourier series representation has infinite number of terms, okay? No computer can deal with infinite numbers of terms. But fortunately, from almost all real-world signals, AN and BN will decrease or converge to zero, okay? So when n is large enough, these two Fourier coefficients, the magnitudes of these two Fourier coefficients will become negligible, which means if you just simply dismiss them, it will have very, very little impact on the shape of the reconstructed x of t, all right? And then possibly I can therefore compress my signal. For example, nowadays, when producing a CD music file, the sampling frequency is 44.1 kHz, which means for every second of our music, we actually have to have 44100 sampling values, and that is a lot. However, for that 1 second of music, which is apparently a signal, audio signal, you can have its Fourier series representation, okay? And you can, instead of acting every term all the way from n to 1 to infinity, okay, let's take a 10 minutes break.